So just as I did not get any response, I'll just say a few words. What is that? What is the problem of best subset selection? It's something like this: that suppose that you have y is the response and you have three predictors, x1, x2, x3. So best subset means it is something like this. So given these three predictors, how many possible regression model you can fit? How many you can fit? So you can fit one regression model with, it's a simple linear regression model, right? Y(x2) and y(x3). So there can be made three simple regression model. And similarly, you can make y(x1, x2), y(x1, x3), and y(x2, x3). Three, like three regression with two variables. And another regression model you can take where you are going to have all three of them. So you can make the seven regression models. You can have one more regression also, that none of the inputs are important. So that means y is equal to constant. So basically this is one, this is three simple linear regression model. This is three regression with two predictors. This is one regression with three predictors. So that means based on the subset, this data, you can build 1 plus 3 plus 3 plus 1 means total 8 regression models. Now, out of these 8, which model has the maximum accuracy? If you consider accuracy to be R square or adjusted R square or malloc CP or AIC, BIC, there are many measures are available. Right? So according to this, which out of these 8 model, which model has the minimum? Say for example, if we have minimum for this, then my important features are x1 and x3. So that is called as, this is the method which is called as a best subset selection. It is a kind of a brute force that you feed all possible models and try to see which model gives you the best prediction or the minimum prediction error, and see what are the features being included into that model. So this is what we call it as a best subset selection. Now, as you can easily understand, if there are three features, then there are 8 models. Mean there are 2 cube models. If there are p many features total, if you have y, x1 and x2, xp, then there are going to be total 2 to the power p many features. So these many models needs to be fitted. It's pretty huge, right? So these many total models. So all you have models with all one variable predictor. So there will be total p many. Out of p many, all two variable predictors. So this is one variable. So this is two variables. So you will have pc2 many, right? And there will have one, there is no predictor. And there you are going to have a three of them being selected, so there will be total pc3 models. Like this, the final one you have going to have all predictors, right? So there will be one means it is pcp. So first one you can write pc0, you can write pc1, and add of all of them, we all know that from binomial, that 2 to the power p. So there are a lot of fitting exercises needs to be done. So to reduce that part is the computationally pretty burden. So to do that, they propose it to be forward selection. Forward selection means that in the first set, so you first fit all p regressions. So means y is equal to x1 and y x2 and y is equal to x3. Suppose this one got to be the best. So in the next regression is going to be y1 is equal to x2 plus x1 and y is equal to x2 plus x3. Now suppose this one you got to the best. So your next step it is going to be y is equal to x2 plus x3. So in the previous step the best model is being selected. So features are being added one by one by one. So this is called as a forward selection. The same process being come from backward. So you start with all model, then drop one by one. So this is called as a backward. Now one of the thing is that, as a note I will put it, that 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 not guaranteed that you are going to get that best model. It is not guaranteed because they are greedy algorithms. What does that mean? So it might happen that there is another. It might happen that x1 plus x3, this may be the best model actually. However, in this process, this model is never ever going to appear, this particular. So whatever be the best selected in the previous way, the same thing is being carried to the next one. So the same way for the backward also. So to reduce that, they have proposed some other thing, another thing which is called as a hybrid, which is a combination of forward and backward. So this is the main idea. What is basically feature selection? The in simple words, we have a data set in Excel file. We have one column response. We have rest of the columns are uh, predictors. We want to identify in a linear regression setup, so which are the predictors are going to be important for us. So this is for what we explained. This is for a linear regression setup, and classification also it is going to be the same thing, because in logistic regression you construct the maximum likelihood function. You optimize with respect to beta. You just optimize this maximum likelihood optimize this likelihood function within that constraint, that whether it is a reach constraint or whether it is a lasso constraint or it is a q lasso constraint or it is an elasticness constraint. The idea is absolutely same. So I'm sure that you have covered the construction of the likelihood for the logistic regression model, and that likelihood which you are optimizing or maximizing, that maximization is carried out under the reach and lasso or the elastic net conditions, and that's it. So these are various different methods which are available as a feature selection in. Uh, so some people, little bit of misunderstanding is there. What is sometimes people also tend to use these principal components. So these are actually derived features, right? Derived linear combination of original predictors. So basically, these are these are very wonderful properties, but since they are linear combination of other features, so individual feature importance is actually lost. So this is not. Uh, this is not a feature selection. It is a kind of interview question also. This is not a feature selection ML algorithm. Okay, so I'm not going into that, since it is not, so I'm not going into that. So let us just get back to one of the some of the demonstration using this. Again, this file will be shared with you, so no problem at all. Can you see the RStudio page?
Yes, sir.
Yes. Oh, okay. So I'm really sorry, since it is an online, because in offline we typically see how in individual PCs are happening. So accordingly we can deal with the things, but we don't have any choice here. So, but definitely it will be there. So please note that this is the this whole thing is being taken from that book ISLR version 2. So it is the section from the section 6.5. So reference is there. So for some case studies, studies which we have. And then you can see our papers on year 10, 2019, 18, and our recent paper Mukherjee uh, 2026. So where we have actually used some of this method, but since it has been utilized for real data and lot of additional things we have done. In fact, recently for one more work we have actually implemented these methods. So, uh, so those are the case studies are there. But since after that you may practice the things on your own, so I thought of taking the things from a known book itself. Okay. So first of all, if you want to utilize it, this is just to depend on the data, that which data you are utilizing. So this is ISLR2 is the package. So let me not install it because it is already installed in my PC and it is loaded also. So I'm not doing installation. So let me just take library ISLR. So there's a data called heaters inside the data. So how do you see that? If we take out the class of the data, it is a data frame. So if you keep names of the data, it is the heaters. So these are the names of the variables. So basically salary, the problem statement they said that they are trying to predict salary is the response. They are trying to predict the salary based on rest of the variable. Now it is something like this, which are the predictors which will be important. So which are the main characteristics of the players which are main determining the salary. So this is something they want to make. So one thing maybe minimum error. One thing maybe their number of hits are very large. One of the thing maybe in which club they are playing. So there may be multiple variables. If you write down this health hitters, it will take you to a health file. So Major League Baseball data from 1986 and 1987 seasons. You see the different variable information also you will be getting from here. Right? The source is also given that. So what is the dimension of the data? 322. So so what is the problem? That we used to predict a baseball player's salary on the basis of various statistics associated with performance in the previous year. This is the problem. So let us try to have a look at what is the this is the distribution, this is the his hitter salary. Okay, as we observe that there are many NA values are there, which is very common. That means this data is not available. Right? So there is a nice function called is.na that talks about which are actually right, that which are actually not available. So where there is a true, these are not available. If I take a sum of this, now total number of true is there. True means 1, false means 0. So there are total 59 missing rows are there. Now there is a nice function called na.omit. There are different ways of treating missing values, but here we are just, since our concentration is on feature selection, we are dropping that part. So we have the na.omit basically function. What it does, so you can see the help file for this. So na.omit, right? Object. So it basically what it does, the rows which contains at least one missing value, it will be removed. So hitters we did. Now see the dimension of hitters. Now it is 263. 59 rows are been gone. Now you have the, now there is no rows. Now if we see that is dot na hitters, all are basically false now. There is no true. Is there any errors? Is there any NA available? Is there? So sum of is dot NA, that's, there is 0. So there is no. So let us first perform this task, that base subset selection, what we have done, right? So let us just have a look at it. We have already learned about this lm function. What is the variable CRBI I think the variable CRBI is number of runs batted during his career. So total how much runs they have made. So whether salary can be predicted or CRBI can be a good predictor for the salary or not, we are just doing a simple linear regression. So it will be salary, CRBI. This is the syntax for this data heaters. What are the coefficients we get? These are the coefficients. Intercept is this. What is the summary? And we see that the coefficients of CRBI is highly significant. And R square is approximately 32%. Right? 0.32. Right? So then we thought that, okay, let us, what is that another variable called at bat? That number of times at bat in 1986. Means how many times he was in the bat. So now we have two predictors. Let us see the coefficients. Yes. Summary of out. So now see that the intercept is no longer important, become insignificant, but both these variables are very, very highly significant. And R square is approximately 0.393 and adjust R square is approximately 0.393. Right? Now what is our goal? Our goal is to identify which are the predictors. Okay, first of all, let me check how many predictors are there. So what is the dimension of predictors? It is 20. So 20 many row columns are there. So there are 19 many predictors apart from salary. Right? So first of all, let us fit a full regression model. Okay. So we are going to utilize library. It's a very nice library called Lips library. You can see the help also for the function rig subsets with certain examples also, and it will explain that what are the inputs, how things to be taken. So this is the full regression, and you know that, right? So this is the syntax, you know. If I want to utilize all variable there, then this is the syntax for that. And let us see what is the summary. This summary, let us read this summary and try to understand what is this summary says. I'm running it once again. Let me take a little bit more, and I'm running it once again. It's not taking that much. This is not enough space, so that's why. Okay, it should be fine. So let us understand this output. So as you see that in the first, if you see the first one, there are blank, blank, blank. Only CRBI there is a star, and then again it is blank, 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 blank. Right? All are blank. So what it says that you see that first task what we are doing. Let me share with it. Let me share with the whole screen. I actually shared only window, so let me share the entire screen so that I can. Yes, the whole screen is shared. So as we observed here, as you see that, right, here we have a P many models to be fitted, right? There we are going to have one of them is going to be best. Like similarly, all possible models we are basically fitting. What we did forward, all simple linear regression got fit, and that got added in the next part. So here x2 got added in the next part. So then again, this many regression to be done. So how to read this output? First column row you see CRBI. So there are 19 many simple linear regression run, and CRBI turns out to be the providing you the as the best predictor. Then we consider CRBI in the next one, and you see that in the next one this hits has come to be the best predictor, right? So then you see that CRBI is still retained over here. Yes or no? Correct. So this is something. So like this in the forward manner, this selection has been done. Okay. This is what we have understood. So this output indicates that base 2 variable model contains only two variables, hits and CRBI. So if you see the second row, basically we say hits is star and CRBI is star, right? It only reports results up. So in general, this reports the, right, only the 8 one. But if we want this all of them, so there are going to be the 19 mini rows. You see that all 19 mini scenarios are being added over here. You observe that CRBI, you see that CRBI is throughout. Here in couple of things CRBI is not, because that probably depends on the predictor, on the accuracy measure also. Also you are applying. We'll analyze it in a while, right? So now let us check out what is the R square. So what are the summary statistics it gives? R square, residual sum of squares, adjust R square, malus CP, BIC, right, rest is not given. Let us see what is R square. Right? So these are the R square. For this first R square is only for when CBRI is there in the model, and here it is the two models are there, two predictors are there, and then the last one when all predictors are there. Right? As you observe that in the end there is not much significant difference is actually happening in R square, right? But always small increment it is happening. So let us plot this as a function of residual sum of squares. As you see that, and residual sum of squares always decreasing, right? It's always decreasing, and after that there is no change. However, we saw that adjusted R square it first increases, and if there is unnecessary variables get added, it may decrease also. As you see over here that the first it increases, then again there is a decrease. So that means there are unnecessary variables being added. Now, at which number of predictors there is a maximum adjusted R square? This is one. At 11 number of variables, it is the maximum. Similarly, we can plot with respect to CP. So we want a model number of variables which has the minimum number of minimum malus CP value. We saw that at 10 number of predictors. So if you see that when it is CP is minimum when there is a 10 predictors in the model. If you check out BIC, BIC is the minimum when we have a 6 number of model, 6 number of predictors. So you see that how important it is. What is the accuracy measure that you are considering? In the same data, if you are using R square, you are getting, which is always decreasing, more and more predictors are there. So, right? So it is going to be better and better. But whether there is not many significant change. Adjusted R square, it will increase as you add up more predictors, but after that it may, because when unnecessarily predictors got added, it again decreases. So and it adjust R square, according to adjust R square, 11 is the number of features to be retained in the model. As per the malus CP, 10 is the number of features to be added. As per the BIC, 6 is the number of predictors which is to be retained in the model. So you have to mention, as you understand that, you need to mention definitely that which is the predictors to be retained in the model and what is the accuracy measure that you have used. Because based on that, your outputs, everything is going to, they may change it. But BIC, Bayesian information criteria, there is some interesting logic behind it. It usually there's a principle of parsimony that it basically penalizes the number of predictors. So they have those, the figure measures have wonderful characteristics and properties. So which in a more statistics uh, course, these things are usually discussed. So let us understand this. As you understand this plot, how to interpret this plot? In some of our articles, actually, we have directly give this plot in our article itself. So these are publication quality also. So this is something you understand in this fashion, that you see that The far lowest rows is the intercept and CRBI. So that means if you are using one predictor, then CRBI is the best predictor. So there are 19 many simple linear regression run and CRBI found to be the best. In the next one is that that you run all 19C too many regression, and out of them you found that CRBI and hits with intercept. These two are together is the best model if you are considering two predictors. So similarly, if you consider three predictors, CRBI, hit, and these put outs, these three predictors. As you go on, see that here CRBI is gone. So that means here you have 1, 2, 3, 4, 5, and 6 and 7. So if you build a 7 predictor model with all possible 19C7 combinations, then CRBI is not there. So you see that with the 7 variable model, CRBI is not going to constitute in the same model. Okay, so this is how they interpret this picture. So as your R square increases, or eventually all models are going to be there. So these are 0.55 it is given, but there is a change is happening after the third digit. So but it is only the 2-digit representation is there. So this interpretation is clear. Now the same thing is the adjusted R square. So as you see that first one retains the CRBI, second one is being hits, then third one put outs, then variables are being added, and here it almost reaches a saturation that all predictors are being added. But after that, more addition is leads to a, so then again the deletion is happening, right? Right. So that means there are many predictors which are actually unnecessary being added. So similarly, you can look at the malloc CP, same interpretation. Similarly, BIC. Right? So minimum BIC for a 6 variable model. So if you coefficient, so if I consider a 6 variable model, which is the minimum BIC, then we get add, bat, hits, walk, CRBI, division, double, and put outs. These are the predictors which we get if I consider the 6 variable model, right? So if I have a 11 variable model, these are the outputs. This is just for looking at there. We can do the forward. This is very nice for rig subsets. We just have to give method is equal to forward. So if you this is the help file for rig subset. So if you see the help file for, you see that method equal to exhaustive. It is the by default. Then backward, forward, and there is another also, which I have not used yet. So this is the, if we do this and if we do the summary, and you'll see that now you'll see the output. So now when you put forward, you see that where is CRBI? Yes, CRBI first got selected, it is true out there. So previous one, what we have done an exhaustive, and which is the called as a best subset regression. But here, see, is a forward regression. So once CRBI inside, the CRBI will continue to be inside. Right, and the end you see that all, as you observe that at the end you have all the predictors inside the model, because it is a forward way it is being calculated. Okay, then you can see the summary of 6 variable model, and you can see the summary of the 10 variable model. So we are encouraged to see whether you are getting the same set of predictors in the final model what you have got by using BIC. So, so this analysis, so you see that why we try to discuss these things in the workshop, because most of the time when we discuss with the students, when we give the project, the students tend to answer that Python has given me this result, R has given me this result, MATLAB has given me this result. And in particular, when we are dealing with applied scientists or project students, it is a very, very common scenario Okay, we have done it in Python and we get these results. Come on, it cannot be like this. These are only tools. But what is the thing? What is the how we are applying? What is the data? Understanding the data, how intelligently we are applying it. It is on us. It is analyzed that what who has to take a decision on that. So that is something very very important. I have found many senior people also they say that no, you do it in Python. It can be done in Python. So the similar thing, it can be done in multiple places. But whether we are doing the right thing or not, that we have to take the decision on that and accordingly write down the things. So this is this actually gives in some time back with one of our collaborator. So they have got an article for some revision. So we said that she has said that they have asked for some kind of applying some advanced methods like neural nets and everything, and other comparisons, lot of comparisons she has said. So I said, okay, let me understand the problem. So when you understand it, I said that it is every condition is being satisfied. So you just apply simple enough that should be done. No, no, no. Then the revision they have asked to do. The reviewer has told to do that. So we have to do it. I said, no, I cannot do that because it is not needed, unnecessary. Okay, but what I can do, I can write a. So then probably they didn't find anyone. So I said that okay, I can write a paragraph for it that why ANOVA should be enough, and this that you report that should be done. So we have written one extra paragraph there with the essential justification that paper got accepted. So many things we go in the machine learning, we probably go by hype. Yeah. Nay, this unless we give this, it is not going to work. I think probably not. As a scientist, we have to take that judicious decision. That we understand the how much risk I am taking. We understand why this method has been applied. I'm not saying this is the best method, but availability of the methods given these different possibilities, this has the minimum error. So I am taking it. And it is not only that, it is not only the only one train test that I result I have got. It is that average risk, uh, the average error is coming out to minimum for this particular method. Hence, I am using it. So on an average, this method is going to perform better on such type of data sets. So that is the confidence we are going to having, right? So that's what is needed. So this is again coming from the backward way, right? You can have the summary for that, and so you can check out that what the backward selection, what is the seven variable based model you get with the forward also whether you are getting the best seven variable or not. So when you are reporting that in some place in some appropriate place, then we must actually ensure also to say that this is the way what we have done it. This can answer cannot be that R has given it or has given it. So that should not be the answer. If the full dataset is used to perform the best subset selection step, the validation set errors and cross-validation errors that you obtain will not accurate estimate of the test error. What does it mean? I only mean here that generally we take the complete data and build it. We many places they don't do the train test, and so that is not going to be a an unbiased. That is not going to give an error for you for your test error rate. So let me just tell you simple things. At least for the statistics people. So I'm not. This is not for others. So you see that many of the approximation methods, many of the accuracy measures, you will see that some measure plus some correction. So this measure which comes from the training from the building the model, you added some corrections. So as you see that this is the behavior of the prediction error, and this is the your training error. This is your train error, right? So if you want to utilize train error as an estimate of your expected prediction error, that means performance of your method on an unseen data, then you need to make some bias correction, right? You have to add something, right? Some bias term to it. so that this curve will be shifted and make it. So most of the machine learning methodologies, that approximation or the approximation of the expected prediction error is usually done by training error plus some bias correction. So for example, MalloCP, for the AIC, for the BIC, many of these methods are actually come out. Where is this? How this bias correction? So typically these correction terms involve model complexity term. So if we want to utilize that training error as to what is called as a to estimate the prediction error, then we need to perform some kind of a bias correction to add up something. Otherwise, we usually call it as a training error, right? Is a train or the accuracy estimate based on training error has a downward bias. This is basically the reason. So if you want to make a bias correction to it, you have to add up something which is typically a function of model complexity. So if you are using BIC, you will have different terms which penalized more the number of predictors. If you are using AIC, which penalizes more on the number of sample sizes. So there are different uh, terms are there which do that. So this is a kind of very intriguing discussion, and one full lectures actually can be given how many of our known accuracy methods, how the statistical ideas actually get uh, get accommodated in the what is called as in the machine learning literature. So that's what really what I wanted to say. So the determination of which model of a given size is best must be made using the only training observation. That's precisely it is. Right here, so for example, this is not there. So I took it from there, but many of the comments I have added for you all, so that later you can understand. So a small of the sample function basically. So now what we are doing, we take the 70% data from that data for the training, and the rest of the 30% we are going to use for testing. So these are the rows we are taking for training purpose, right? And then, so this is the data which contains only the training data. So this is the training data, and this is the test data. So what is the dimension of meters and train? It is 134 by 40. And what is the dimension of meters test rows? This is 129. So typically this should not be done in general, but typically what you need to consider, you have to consider. So I did not, here only it is 70%, but here we have taken a almost equal part of this. So approximately equal part of thing true false has happened here. So this is something what we have done here. So plain prediction of training sample starts here. This is only for demonstration. Okay. So then again we do the same thing. See that now data we are passing heaters only the training sets. Let us see. Right? You take the summary. So this is we know how to do the summary. Now test. Now we are going to test it, right? On the heaters data. So what are you? This is the comment by which we can test it. So the model.matrix function is used in many regression packages for building X matrix from the data. So what is this? This is what is the predictor values. Then let us calculate the errors for it. There are 19 many predictors. So what are you computing? We are computing errors from all of them. So that means Peter's salary in the test data minus what I am getting from the predictions. And then I'm storing the value of the errors. So let me execute this. And these are the errors that we have got. So this is the test error. So you understand that. some part of the data we kept is a training, some part of the data we take for a testing, and this is the test error. So we build the model, and what is performance of the test set that we are doing. So it is the average we have taken of the prediction error. Which is the minimum? 7. So this is the model. This 7 variable model turns out to be the minimum one. Right? Now note that this is probably not written there. So note that as my training sample changes, the selection of the best model might also change. That means it is a random selection of training points, right? So if I do the same experiment, I may get a different set of training points. So according to that, my best model, what are the predictors will come up in the model that may be different than yours. So therefore, it is always suggested to perform it multiple times and taking average of that, so that this will be the risk will be less. It is always suggested that you do this process for some repeated times and take an average of the test error. However, this may not be feasible for a big data scenario. When you have a GBs after GBs after GB data, there it may not be always feasible given your computational. Because we have done this in our the 2018 paper. This is the process we have done it for analyzing distribution of species and making their prediction under climate change. So this process we could do only for 25 times, and typically one run used to take almost 9 to 10 hours in our server in the Department of Mathematics. So this is something to be kept in mind. So here as this example, I'm just doing it for doing it 50 times. And then I'm getting to this test error. You see that this is the distribution of the test error. So across, you see that across different samples, training samples, see that so much huge variation in the test error is happening. So what is the average test error? I take the column means, the means of all these columns that I want to take, and then we plot it, right? So this is the average test error. It seems that at 10 subset uh, gives you something kind of an optimal results, right? So there are certain things that we can actually construct a function also for these and do this whole process. So that is something been explained there. I'm not getting there. So based on the training data, suppose that you obtain the best seven variable model. However, you need to use the full data set to get a more accurate estimate of the coefficients. So note that we perform best subset selection on all the full data set and select the best 7 variable rather than simply using the variable that are obtained from the training set. Because the best 7 variable model on the full data set may differ from the corresponding model on the training samples. This you have to keep this in mind. Right? So here, if we see the coefficients, in fact, we see that the best 7 variable model on the full data set has a different set of variables than the best 7 variables from the training set. We just build a training set by using 134 rows from that. There, what is the best 7 variable set we have got? In fact, if we apply this subset, it is going to be different, right? So another method is that k-fold cross validation. So we perform a k-fold cross validation on a subset within each of these k-folds, which I have already explained. So this is what is the okay. So this is the code which performs the k-fold cross validation, right? And then right, then you plot the mean of this. So you see that using cross validation, it seems that we are ending up with a best set of variables that if my model has 10 many predictors, this turns out to be the best model for this. Okay, so this is something an example which we have put over here. let me like you can continue with this and run the course and something you will be understanding. Now let us talk about that feature selection that we have planned to do, like using the we have learned three methods. One is lasso, one is ridge method, and another one is the elastic net, right? So this is can be done. This is GLM net is a very very wonderful package in R. This provides a extremely uh, what is called as a powerful tool to perform all these analysis. So what is that? As we say that, if we recollect this picture, you have to choose different choices of lambda. You have to choose a grid of values of lambda, and in each of the grids you have to calculate the cross validation error, and you see that at which lambda value the minimum the cross validation error is minimum. That is the choice of the lambda value that you need to take for your uh, for the final output. So here also we have done actually the same thing. So we have taken a grid of values. As you see that the values are usually taken to be small. Some values we have taken in fact pretty big. So 10 to the power 10 and to the power minus 2, right? Length is equal to 100. So we take in the powers of that. But in general, the values are taken to be small. It should not be very large because you are actually imputing it. But this is for demonstration. It's being taken like this. Now you observe that. So what we have said, if you recollect that, so when we are writing that summation I is equal to 1 to n, yi minus summation j is equal to 1 to p, xij and beta j whole square plus lambda times alpha times summation beta j square 1 minus alpha times summation beta j mod, right? Correct. So instead of writing this, maybe let me write down in this manner. It will be clear right now. Now here, if you put alpha is equal to 0, that means only the square term will come. So that means it is going to be reach. If you put alpha is equal to 1, that means this will go to 0. That means this is going to be lasso, right? So in that function is GLM net, you put your x, you put your y, and alpha is equal to 0. Alpha equal to 0 means it will perform a ridge regression. So you see that by default GLM function performs ridge regression for an automatically selected range of lambda values. And this lambda values that is given over here that you have to pass in the grid. So you pass this lambda values on the grid. So then, however, here we have chosen to implement the function over a grid of values. So here we have given a grid of values. So for example, let me execute this. What is saying x should be a matrix with two or more columns. So let me check out what is x or this is our x over here. So whenever you are running it, you have to ensure that x stands for the matrix that the input data you are giving. So what is my headers data here? This is the headers there are lot of, right? So if I take a head of this, have a look at this head of headers data. So this is the data that we are getting, right? And what is being said that the first one, this one has to be a matrix. So and y, what is y here? Let me just check out y. So these are the values corresponding to y, right? And let us check Peter's dollar salary. Yes, this is the same thing. So y and salary They are basically same thing. Now you need to create that x. You have to x pass the x over here. So first let me read out the error once again, because if such a scenario arises, then how would you deal with it? So this is an error I observed. Error in this stop x should be a matrix with two or more columns. So that means x has to be the matrix of the columns. So let me write down first x is equal to heaters minus salary. So first of all, name, let us check out what is the names of the heaters. It is salary, but S is capital S, right? So let me execute this line. Okay. What it is saying, salary invalid arguments of the unitary operator. Okay, no problem, madam. So what I want to do from this, I want to remove this the salary column. So another way is that if you write down minus is the 19th column is the salary. So C of 19. Okay. So now let me check what is the names of X. You see that there is no salary, right? There is no salary. So here drop the salary column, right? So no salary. Now you check out class of X. It is a data frame. But the error says that if you check out the error, it says that it should be a matrix with this. So that means you need to convert X into a matrix. So as dot matrix X. So there's a nice function called so convert into a matrix. This is a data frame. The argument is needed converting to a matrix. Now if you again check what is class of this, now you see it is a matrix now. Now let us see whether it runs or not. Right? So what it is saying that now let us see check out the output. Yes, we have got outputs and everything. But what it is saying that there is some NA values are already are there. So let me check my variable column matrix X. So is dot NA in the matrix X. There is actually no, right? Yes, there are, right? There is actually no, but why that output? Why there is a warning? So now understand that is a warning. What it says that in stores see the double NAs introduced by coercion. So did it impact the outcome what we have got? So this is a so check that. See that there is a warning as why I'm writing these views, these are the part which is very important. That whatever we are applying, whether everything is going into the right direction or not. Because even the slightest thing we cannot compromise, right? So you have to find it out that why actually this is the thing is given. The simple hint is that is all the variables are numeric there. This is the only simple hint that I have given you. So check out hint. Take all the variables, all the predictors, and their types. To be able to find it out. So this is the output that it has run. So what is the coefficients that we are getting? These are the coefficients. That these are the coefficients. Lot of coefficients we have got. What is the dimension of this? Right. So you see that, right? Why is this so much of that? Because it has been calculated at each of the grid values. Right. So these are the only three. Right. So how many grid values are there? A length of grid, right? So what is the calculation has been done? Let me just take out you here. So this is your lambda 1, this is your lambda 2, this is your lambda 100. So here you got 19 coefficients. So coefficients 1, 2, like this 19. So here also you got coefficients 19. Here also you got coefficient 19. So your output is going to be a 19 by 100 matrix. Okay. So these are the coefficients corresponding to lambda 1 for lambda 2. So that is the output what it is showing over here. Is it clear? So please don't feel that. So here note that. So each column contains coefficients for different grid values of lambda. I'm writing over here, okay? These are the coefficients that we have got. Right? So this is for when one value is lambda, then what are the coefficient values that we are going to get? Right? In coefficients, and let us make a plot of this. So these are the coefficients actually, how the plot of these coefficients looks like. This is the coefficients. So this is for the 50 when you are at the 60th one, and this is basically where it is the 50th one. This is very interesting plot. Check out, this is the plot. This plot basically, sometimes this plot is being represented also in articles, that how actually this predictor. So each of the line corresponds. There are 19 of such lines. Each of the predictors corresponding to, so they are eventually getting shrink and eventually getting getting smaller and smaller and smaller values. Right? That how those guys are shrinking, that is something being represented over here. Okay. So next part is that, so the same procedure is being done using a train test validation, and similarly this is the simple piece of code, right? This dot print. Again, I think that x is now getting changed, right? Here, what is the dimension of x? 263 is the dimension. So the original x they contain actually, in fact, some of the NAs are there, some of the missing values are there. That may be a reason. But again, tell you that correct. Uh, take care of the state values stored in X. So these are something when you are, because these are not uh, programming languages which is case sensitive, in a sense that, like, what is the last object that you have, whether you're writing capital X or small x, these are many changes, many things you have to keep that in mind. So if we try to decode that, it is saying that error in evaluating the argument x in selecting a method for function as dot matrix object of invalid type character or matrix text. So what is this help DLM net? If we go over there, you will see a lot of inputs, lot of arguments are there. This is a very powerful tool. So this input matrix of dimension in observe into inverse, number of observations into inverse. Each row is an observation vector, can be a sparse matrix format also, inherit from the sparse matrix in the package matrix. Right? So what is the problem is happening over here? Let me write down is dot numeric false. So what is that class of x? When you give class of x, it's a matrix it is giving. Right? If we print head of x, are you identifying what is happening? Good that this problem has appeared, because most of the time this is one of the reason where this is a very common mistake when we are trying to run any algorithm. This is a very common problem that we face. What is the problem? Can anybody tell? That this is basically coming up as these values are being coming up as a what is called as a numeric, sorry, as a character. These values has been considered as a character itself. Let me just elaborate this. What has happened? Let me just take out over here. So what basically has happened? Say for example, you take you take three rows, or maybe I am writing a matrix. You take three rows. A is equal to C 1 2 3, and B is equal to C 2 3 4, and C is equal to, I'm taking say A, B, and C. So you know what is class of A? It is numeric type. And you know what is class of B? It is again numeric type. You know what is class of C? It is a character type. Now suppose that I thought of storing these values in a matrix. So let me call this a matrix M. Matrix data is equal to C, right? And I'm putting A, B, and C. And how many number of row I want to be 3, and number of column I want to be 3. So if I print this matrix M, sorry, as you see that all have come with inverted comma, right? So if you just print A, inverted comma, print V inverted, but if you print C, there is inverted comma. So characters are understood by inverted comma, and whereas this what is called, whereas the numerics are not understood inverted comma. But in a matrix is a data setting where all of them has to have the same data type. Whereas if you are having a data frame, they may have a two different column, may have a two different data type. In matrix cannot store two different types of one type numeric, one type character. This cannot happen. So everything will be converted into character only. So this is what has happened over here. So if the original vectors, if you see, these are actually the right. So this is the thing which has been converted into a matrix. Right. So you must need to take care of this. Such scenario should not occur. Okay. Now, natural question is that what to do if such a situation has come? What actually to be done here? Okay. Can anybody tell that we are going to have? Say, I'm just writing it over here. I think I have a simple explanation for this. Let me go this way. Right? So you have some columns. If you observe that some columns in your X which contains actually the characters. So, but if you want to apply reach or lasso, these characters has to be converted into a what is called as into numeric vectors only. So that must be carried out. So before that, what you can do? There are multiple ways. One is called as one-hot encoding in machine learning literature, or it is also called as a dummy encoding. So that means we created one more. So from one column, it got converted to three additional extra columns. So 100 means it is A. The first entry is A means it will leads to 100. Second entry is C. This will lead to 001. Third entry is A, again it is 100. Fourth entry is B, this is going to be 010. So this is called as a one-hot encoding. So there are three different classes are there in that observation. So three different new columns being created. Now note that sum of row is equal to 1. So basically by this process, you create three additional columns. However, sum of rows, all the sum of all the not row, sum of all columns is basically 1. So that means they are linearly dependent. So this is the one what is usually called as a, infuses multicollinearity. But however, region also they do take care of it. There is another thing also called as a dummy encoding. That means 1 0 represents, if it is C, that means 0 0, and if it is A means it is 1 0, and B means it is 0 1. Again A means 1 0, C means both are 0 0. Now you observe that some of the columns are not, so the columns are independent. Understood the process? So let us just have a look at the original predictors. So let me check out. Let us take the hitters data, right? So head of the hitters data. So what are the predictors? Okay, these are. Let me have a view also have a hitters data. Okay. Yes. So this is the view of an hitters data that we are getting. So along, these are the names of different players and these are their statistics. Now note that these are the very predictors that league, division, like a new league. So they are basically comes from different. They are not numeric in nature, right? So you need to ensure that appropriately the new columns are being created. So either by what encoding or by dummy encoding for each of the variables, new columns are being created, and accordingly then you have to create the matrix of that, then you have to pass on to the inside. So let me check out just what is the predictor which is for the link. But if I write down hitters, right, to see that this is something like, so how many, this is, it is a character type, and levels are, there are two levels which is A and N, right? So you have to convert it to another two new predictors, and this is going to be taken care of inside this, right? So is that clear? This is the process that needs to be carried out. So what I can do here, what I'll do here, so let me just to remind it myself. Remind it myself. We're going to change the x we need to ensure that x is that the columns character columns of the data keepers converted to numeric columns by using encoding or dummy encoding. So this is the first thing. There is a note, and secondly, the same X matrix. So why this part? This is the part I have taken. The reason is that if you check out many of the, because in any of the, when we talk to our industry people who are basically use pythons and everything, lot of, because uh, many of our students projects are actually are being associated with industry. So when the industry teach them a machine learning pipeline, so when they are considering a treating of the handling of the data, or first look at the data, then this is the part they always do. So which typically part is a one code encoding. So this is the part of the data preparation before we start up with any machine learning algorithm. Please understand it. This is very, very important because before applying any machine learning algorithm, you have to ensure that all your predictors, these are being converted into appropriate numeric features. However, the same matrix, since we are using R, SMLR, right? Statistical machine learning with R is for a long time people are using it. It is pretty intelligent. So, however, if you are using R, that needs to be done. The same matrix can be obtained from the model dot matrix, which this I will add this. This file is already there, but I'll just write it and before sharing it to all. Okay. So in that case, if you don't do the one-hot encoding part, that is also done because the matrix, the GLMNet package is intelligent that even if you are passing that passing what we call it as a the whole data without doing this preparation, it will convert the characters things into a what is called as a. Yes. So what are these files? Rest of the things are contained. So this is the reach part, and if you go, this is the reach. And this is the part when we put lambda is equal to 1, then this is the part which stands for the lasso. So what is that? So if you put here, where did it go? In the same case, if we give here alpha is equal to 1, so this guy is going to be 0 and only this term is going to remain. So this is called as a, this thing is what you do is, this is called as a lasso, and this is the way how we can get the coefficients of lasso. So what I will do here, just leave this part. So what we can do for a simple demonstration here, I can post, let us see what is the heaters data. This is the heaters data, right? And what is the names of the heaters data? This is just for demonstration. That add bat. If I take say for example, if I take columns till first 10 columns, maybe I can take. Okay, first 10 columns. So if you see that head of heaters, first 10 columns, 1 is to 10. So they all are basically numeric uh, in nature, right? So what we can take? We can take a temporary data, which is basically heaters. Okay. What is that? First 10 columns I am taking. So this is the 10 columns I am taking. I am calling it X, and I am converting it to a matrix also as dot matrix. We have got here X, and we have got a Y. What is Y? Y is basically the salary. What is the dimension of X? 63 by 10. What is the length of Y? It should be 263. Yes, 263. Now what we can perform there? We can perform a this quantity. We can perform a, what we did here, we have taken only the first 10 variables, and alpha equal to 1 means it will perform lasso, and we have performed pass that grid. If you just plot this out, see that this is what it says, that how these variables are basically getting string. So how these variables, how this first of the 10 one getting close to 0. This is something very, this picture is very like some of the articles we have in fact given these pictures also. Okay, so this is something what we call it as a like how the path algorithm works and how those, which are the parameters gets into 0. Now what you can get, you can get the coefficients of this lasso as well. So let me not take this one. So s is equal to some particular value, say I have taken, say for example this. Mm, just only take down the lasso coefficient. I'm not doing the prediction right now. The lasso, and we can take up the coefficients. Right? Take down this coefficients. We are storing it and predict out, and type is equal to coefficients. So print this lasso dot coefficients. So these are the many coefficients which we have got for different all grid values. So it seems that for many grid values, many of these coefficients are eventually they are getting off. They are getting zero. Okay. So please note that this grid values that which it has been utilized over here, this is a very large grid point. So typically we consider very small values of the grid points. So this is something very important. Here in this particular example, I can see that one. This is the plot which I have told here that this is the plot for this particular example. I am not able to get it over here. I'll check out that why this plot is not coming, but I'll show you that just before finishing. I'll show you that how the plot looks like. We just have a simple example. Just solve the case study using this. Let me just check out whether I'm having this or not right now. Yes, I am having it. So let me just check out. As you see that I usually create uh, these files where we are doing any kind of data analysis. We try to create this and hope uh, this will run without error. I just want to show you one more one of these plots. Okay. There is some error I have encountered, but there is a saved file for this. Let me just show that to you. I'll ensure that adding that part in the document. Yes, got it. So this is the plot. As you see that, like this one case study recently we have done. So as you see that how with different values of lambda, the different coefficients are getting diminished. So these guys are getting zero, and this is the mean squared error for different values of lambda. Here it is put in a log scale, and whichever the minimum lambda that is being attained. So this is basically the plot with respect to lambda. So this is the plot what I have talked about. So this is the plot. These two plots are very important, and you can, if you are applying lasso, you can utilize these plots in your reports, in your, in fact, in journal publications, wherever you are submitting papers. These things can be done. Okay, so I'm sorry, this document I cannot share with you, but because this is just yet unpublished, so you just have solved some of the interesting problems. But I would definitely ensure that in this, where did it go? So here, I definitely am going to ensure that in this document you are able to see this particular picture when all the variables are being included inside the model. So we have covered reach, lasso, best subset selection. Also, we have performed what is called as a elastic net. Just in automatic question comes how to perform elastic net. If you see this document where my writing things, if you put alpha is equal to 0, it becomes reach. If you put alpha equal to 1, it becomes lasso. If you put any value between 0 and 1, that will become what is called, that is going to become what is called as a elastic net. And again, the best choice of alpha is usually considered by using what is called as a cross validation. So again, I'm writing as a note. So here I'm writing a note. So if GLMNet function, this document will be shared with you. We use alpha is equal to 0.3, it will perform alpha in 0, comma 1, it will perform elastic net. And the usually optimal choice of alpha lies between this is obtained by cross validation. Again, that's the again with respect to alpha, you can actually draw a cross validation error profile, and that is being used for this purpose. So I think with this different dimension, different aspect of feature selection I have tried to cover. I'm sorry I could not actually take you to the Bayesian connection of this feature engineering scenario, because when we talk about this reach, just as a hint, I'm just giving. When we are actually where is the reach things comes up. Yes. When you are talking about reach, so if you consider a prior distribution for your coefficients as a normal distribution, then what is the solution posterior distribution of beta you get? The posterior mean is exactly the same solution what you are doing getting by this optimization. Another one is that if you consider a double Laplace, the Laplace distribution for your parameter beta, then the posterior distribution of beta that you are going to get as a solution of the lasso optimization problem. So this only I could uh, I could say that, but I think I'll probably share you this document which sometime back I had written for understanding for the students. You'll find some of the problems probably here. So please note that these are not copied from anywhere. These are written by us only. So here are some of the many examples you'll find out. And at the end, at the module 5, we'll find some Bayesian connection to statistical regularization. So what we have done over here. So this is a simple document that I have tried to write it down in own language. So as you see that this is the one actually what you are doing in Reach. So this is actually the minimization what you do. And this the solution of this posterior median is actually going to be the solution of the Reach. And similarly, this is for lasso. This is what you do. And I try to give little bit of derivation also here, that if you consider this is the prior, and if you write a hierarchical form of this, then apply the base, do all the calculations and everything. Eventually, your final solution turns out to be like this. So this is going to the posterior distribution, and this is going to be the solution of this. So as you observe that here, there you had a lambda, right? And here we have, instead of lambda, we have a sigma square by c. So if you want this document also, I can share with you. So should not be any problem. So this is actually the solution for this, where lambda is basically sigma square by c.